All right, so finally, at long last, we're going to start chapter seven. This is, of course, brand new content, and what we're going to be looking at initially is several key applications of integration. Okay, so we spent quite a bit of time reviewing integration, so the timing is perfect. Okay, so let's take a look at what's first. So this is section 7.1, and here we're going to see some extensions of what we've been doing up to this point, specifically areas, not just under curves, but between curves. Okay, so we're going to extend what we've been doing so that we can handle other situations besides just finding areas under a curve down to the horizontal axis. Okay, now, luckily, what we're doing here, none of it is really new. It's just a different way of applying what we've seen up to this point. So anyway, what we're going to do is look at the area between two curves using integration. And later on, what we're going to do is extend that to volumes. Okay, that should be interesting. All right, here we go. So here's a graph that illustrates exactly what we're about to do. And you can see that unlike the past examples we've had recently, um, that area doesn't go all the way down to the horizontal axis. Okay. And so that raises the interesting question, what do we do now? All right. Well, you can see the two functions cross within the interval of interest, which is, of course, from A to B. And so we'd like to know how to find this region between them. So it's a very simple idea. What we're going to do is first note which curve is on top, and that would be the f of x, and then which is on the bottom. And then what we're going to do is think about it this way. If I were to just look at F only, all the way down to the horizontal axis, it would be easy to calculate this area because all I would have to do is find the definite integral between the two endpoints, and we'd be all set. Okay. Now, if we did the same thing for G, between A and B, the area would be the integral from A to B of G of X, of course. So basically, in terms of geometry, what we're going to do is take one and subtract the other. Because if you bring them together, you'll see that, let's see if I can draw this properly. So once again, f of x is the top curve. Then we have g of x is the bottom curve. And that crosses at A. Actually, it crosses outside of A and B. A and B are in the center there. Um, so let's say that this is A and B. So the area under f of x is, we'll color it as black here. Then the area under g of x, I'll change that to red. Um, oh, I thought it was going to go to red. Hold on a second. There we go. Anyway, the bottom line is whatever's left over is what we're after, and that would be this piece here. So what are we going to do? We're going to subtract one from the other. And that's all there is to it. Okay. So actually, let me move it down here to make it a little neater. The area of interest is the integral, the definite integral between a and b of f of x minus g of x dx. The thing is, we've got to just make sure we know which is on top of which. In other words, if we get them backwards, we'll get a negative area. That's how we'll know something's not right. Okay. So let's see if they have any specific examples here for us. And yes, they're doing the same thing I was trying to do. They're showing you how this works. So the area of interest in this last case is this blank area, and it's just the difference between them. Now, what they're going to do though here, in order to extend this to other cases, actually, let me just see if they have an example here. No, they've just got a lot of theory here. I'll tell you what, let's make up an example of our own. Um, how about this? Actually, I should have called this f of x. So we have f of x on top is x squared, and this becomes our g of x. Okay. And let's say we're interested in the region between, let's keep it simple, 0 and 1. Okay, so A is 0, B is 1. So the area in between these two curves, which does not reach all the way down to the horizontal axis, that's the key to the whole thing. Um, so f of x is the one on, actually, in this case, g of x is the one on top. All right. So again, if we got it backwards, we would know right away because we'd get a negative area, and that would be a signal that we should get reverse the two. So we have negative x squared plus 2 minus x squared dx. Okay. All right. Now, of course, we can apply the rules that we've learned up to this point or have reviewed and evaluate each of these. Actually, let's call this one. Hold on. Let's factor out the negative 2x. Oh, no, no, no. The 2, sorry. Not the 2x, the 2. All right, let's try that again. We're going to factor out the constant negative 2. And then here we'll simply have 2 dx. Okay, so now we're good. Okay, then we can simplify this in just a little bit. Um, yeah, that's right. Okay, now, of course, you know that we're, based on the fundamental theorem of calculus, we're going to just evaluate at the two endpoints and subtract one from the other. All right. Oh, I almost forgot the negative here. Sorry. And then we're going to have minus 2/3, 1 minus 0, plus 2, 1 minus 0. So we'll end up with negative 2/3 plus 2, negative 2/3 plus 6/3. And ultimately, we end up with 4/3. Okay, so it's that straightforward. You're just literally subtracting one definite integral from the other. Just make sure you get them, in the right order. That's all. Okay. So this is what this section is all about. So what this does is it expands the number of cases we can analyze with definite integration, whereas before we could only look at curves that went all the way down to the horizontal axis. Now we can do more than just that. Okay, now this is where the theory gets involved. They're going to say, well, listen, how could we extend this even further to other cases? Well, let's take a look at this curve. And you'll see what they're basically telling us is that, like when we were reviewing integration, we saw that integration under a curve down to the horizontal axis. What are we actually doing to find, let's say this is f of x, and we're interested in this area here. What are we really doing here? We're creating a series of rectangles. And in the limit, the areas of these rectangles will equal the area under this curve. Okay. But here, what they're saying is, well, we can do something similar. We can define rectangles in this area. And here, each one will have the same width. You can tell because there's no subscript. It's just delta x. It's a constant. And so we break it up into n equal rectangles. Of course, each one will have a different height. And in this case, the height is the difference between the top curve evaluated at xi and the bottom curve. Okay, so we have a series of rectangles. So remember, it's just the width times the height. Which means delta x f of xi minus g of xi. And of course, if we add them all up, we'll get the area, the approximate area between the two curves. Yes, and they're calling each one of them the ith subinterval. Okay, that's the number of rectangles. Okay, so then, of course, if we take a limit, this is what this is all building up to. This is basically just a justification for what we're doing. Let's get this on the notes. Okay, so this is just like the way we define integrals in the first place. As you increase the number of rectangles, which means delta x is shrinking, um, the limit of all of these rectangles added up is the integral that we're looking for. Okay, so this is how we define integrals in the first place. So it stands to reason that this is how we would find the area between the two curves. Okay. Now, by the way, they're going to continue to use this approach to generate other results as we go along. And so this is our area. Now, if you notice, they are assuming, by the way, that f and g are continuous, which means there are no gaps. Okay, otherwise this result does not hold. But if they do, and then we're defining them over this closed interval a to b, and we have to make sure that one curve is always above the other, at least within that interval. Otherwise, we have to do something different. Then this is all we have to do. Okay. If they cross each other, then we have to essentially treat each region separately. And I think we're going to see some examples like that very soon. All right. Now, they want you to notice that here the entire region was above the x-axis. Here they're making the point that it doesn't matter where we are with respect to the vertical axis. This works if the curve is partially above and partially below the x-axis, or if it's completely below, it still will work correctly. All right. Oh, here's one. All right, they finally gave us an example. Let's try it. Um, X squared plus 2, which of course is a parabola, and then y equals negative x is a straight line. Let's try that. And the interval of interest is 0 to 1. Okay. Whoops. All right, here we go. So this is what we're after. All right, so, we can draw our own little sketch. Or maybe not. Maybe I'll just steal theirs. So in principle, you should confirm that both of these functions are continuous. And well, you can see they are. One is a parabola, one is a straight line. And also, what's important here too is that within the interval of interest, one of this is always above the other. Okay, so here they've designated f of x to be the parabola and g of x to be the straight line. So this is our quote representative rectangle or subinterval. Okay, so that means we can go ahead and find this area as the integral of 0 to 1 f of x minus g of x, which means x squared plus 2 minus x, all of that multiplied by dx. All right, now the rest of this is just a question of simplifying it and then applying the rules of integration. And of course, at the end, applying the fundamental theorem of calculus to solve for the actual constant value. So minus x is plus x. So let's rearrange it, um, make it a little neater. And then we can go ahead and integrate it as three different integrals all added up. With this one, I'm going to factor out the 2, and then I'll apply the power rule to each of these cases. And we don't need the c because this is what we're doing is a definite integral. So we'll have x cubed over 3 evaluated between 0 and 1 plus x squared over 2, again evaluated between 0 and 1. And then here we simply have 2x evaluated from 0 to 1. All right, so let's do the substitutions. And this one is particularly simple because one of the lower limit of integration is 0, which makes things a lot simpler. Okay, whoops. I still prefer writing on the whiteboard, but I hope I'm improving here with this thing. Let me get this out of the way. All right. And the last one is There we go. All right, here we now we just combine them. So we need a common denominator. Let's choose 6. Um, and we end up with 17 over 6. Okay, good. Beautiful. And yes, so they agree with us. It's 17 sixths. Let's see. Now, here they oh, I see what's different here. They cross each other. Um, hmm. I'm trying to figure out how this is different than what we just did. Um, oh, I see. No, 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 because here the two curves never intersected. Oh, okay. I was for a second, I was like, what are they doing here? So yeah, here we go. But it's the same logic. It's the same exact setup. All right. Well, clearly f of x is on top. The interval of interest, um, oh, I see. You know what's different here? Because they're not giving us an interval. They're saying just find the area between the two, and we have to figure out where they cross. Okay, now I wasn't quite clear about how this one was different than the other ones. They're not giving us any specific interval to choose from. They're saying, listen, you find the endpoints, and then wherever they overlap like this, then you find that area. Okay, so the first thing we have to do is find where they cross, and that will determine the upper and lower limits of integration. Okay, so good. Let's do this. F of x is 2 minus x squared. Okay, but keep in mind, well, all right, that's the one on the top. And then we have g of x is just x. All right, so where do they cross? Well, clearly, there are 2 points where they cross because one of them is a parabola. So we'll just set them equal to each other. And we'll find that there are two solutions, of course. I'll tell you what, let's do this. Let's get 0 on the left. So I'm adding this to both sides and subtracting the 2. And now I can either factor or I can use the quadratic equation. Let's factor. It'll be a little quicker. So that means that each of these individually can be set equal to 0. And therefore, I end up with x equals -2 and x equals 1. Yeah, and we can solve. It doesn't really matter what the y coordinate is here. What matters is that this is act 2, -2 rather, and this is 1. So what I'll do instead is this. And now we can apply the technique that we've been using, except now we know that we're supposed to use the range from -1 to 1. Okay. Sorry, -2 to 1. So the area will be this. Okay. All right. So once again, f of x was 2 minus x squared. And g of x was x. Okay. All right, so this will be very straightforward. So we've got, we'll rearrange this algebraically, and then we'll integrate it. All right, of course, we'll apply the power rule. In the last case, um, well, we have the constant dx on the inside. The integral of dx, of course, is just x. So we'll end up with, oh, sorry, what am I doing? This is x cubed over 3. Let's fix that. Much better. And then here we'll have x squared over 2. And then here we'll simply have 2x. And now I'm going to factor out those constants. That usually makes things a lot simpler. And this one is just 2x. All right, now we can make the substitutions. Okay, so you got to be careful here. I mean, there's so many opportunities to make mistakes, especially with signs. Um, just keep in mind, so we factor out the constant. So because this is x cubed, what you're actually solving for is 1 cubed minus 2 cubed. In this case, it's minus a half times 1 squared minus 2 squared. And then down at the end here, we have 2, 1 minus 2. So there's a lot of negatives in there. So keep your eyes open. Now, of course, negative 2 cubed is negative 8, but we're subtracting it. But now here we're subtracting 4. And here 1 minus 2 is, of course, 3. All right, so we're getting there. All right, good. Now this becomes minus 3 plus 3 halves plus 6. So we'll need a common denominator. Let's do 2. And so here we end up with 9 halves. Beautiful. Okay, so let's confirm that. So yes, we get the right interval. Yeah, we did everything right. It's fine. All right, good. Uh-oh, what's going on here? Look at that. The curves are not on top and bottom, but left and right. What do we do now? Okay, well, this is where we have to approach things a little bit differently. If you look carefully over here, the way this graph is written, these are now functions of y instead of x. What we're going to wind up doing is taking the curve that's to the right minus the one on the left. Okay, so let's see how that works out. So now that came out of left field, but yeah, no, I mean, there's no reason why we can't do this process from left to right as well as top to bottom. All right, so now the functions they gave us are actually x equals 3. That would be this one down here. 3 minus y squared. That's what happened. And then they also gave us x equals y plus 1. So if you notice, what they're doing is they're calling x f of y. Oh my God. And then this one becomes g of y. Ooh, now that's interesting. Now, also, they're expecting us to find the points of intersection. So we'll do that right now. Y plus 1. And of course, you can see there's two of them because one of these curves has is a quadratic function. So y plus 1 equals 3 minus y squared. So we're going to have a quadratic expression. Let's add this to both sides. Then I'll subtract the 3. Okay, that's good. Then I can factor. All right, yeah, I've got to be careful with that factoring. Set these equal to 0 individually. And I end up with -2 and +1. Let's take a look at the graph. So here, -2, but the actual point is -1, -2, which we can solve for if we plug in -2 into either of these two equations. And then this one is 1. But keep in mind that's the y coordinate. So here's what we're going to end up doing. Now, the g function is the one on the right. So we're going to do this. Area equals the integral, and we're using the y values, -2 to 1, and because g of y is the curve on the right, that comes first. And then the variable is dy. It's not dx, it's dy. Okay, everything's in terms of y now. So g of y is, once again, 3 minus y squared. F of y is y plus 1. So now the rest of it is exactly the same as what we've been doing. First, we, of course, rearrange this algebraically. Then we write it a little neater. -y squared minus y. So 3 minus 1, of course, is +2. Now we integrate with respect to y. And then we can simplify them a little bit. Um, yeah, so let's do this. Let's factor out the constants. Okay. And then, of course, we apply the power rule. and evaluate between -2 and +1. So it's not a very complicated integral. It's just the idea here is the setup is what we're really trying to learn about here. All right, here we go. Actually, you know what I'd like to do? Just because it tends to get very messy, I'm going to factor out the denominators as well. Let's do that. The simpler we can make it, the better. There's already a million opportunities to make mistakes. All right, now we should be okay. Oops. 1 squared. Oops. Yeah, I don't know why that got squiggly down there. Hold on. There we go. Just want to make everything as neat as humanly possible. All right. So let's figure out what this is equal to. So we're subtracting now. -2 cubed is -8. And what do we have? -1/3. 9/3, of course, is 3 plus 3/2 plus 6. If we convert these all into halves, we have 9/2 again. Okay, now what's going on here? Well, they've kind of pulled a fast one on us because um, they just sort of flipped it over with respect to the horizontal axis. But um, this is what we ended up with. So this way we've got the same results. Um, what they're I guess what they're going to get to eventually is the idea that for some cases at least you can choose to do either left to right or top to bottom. It actually makes no difference because you'll get the same results anyway. But something like this, because of the way the curves are shaped, you might find that it's better to go left to right than top to bottom. Okay. So anyway, now here they just want you to see what's actually happening when you do this process. Um, just quick, take a quick look at this graph. If you're doing this now, this is going back to the days when we had a curve over the horizontal axis. They just want you to visualize what's happening here. This representative rectangle, they keep shifting it to the right and including more and more area so that what we're doing is essentially filling in all these rectangles until we have everything in place. And this is our final result. So in other words, if we started with the curve, this is the function here was 4 minus x squared. But since it's reaching down to the horizontal axis, we don't need to subtract one function from the other because, it's just y equals 0 anyway. So from the range to -2 to 2, so We certainly know how to do this one. And we can rewrite that ever so a little bit simpler. And what do we get? All right, let's see what we have. So 2, obviously, minus 2 is 4. Here we have 8. Now, minus 2 cubed is minus 8, but when we subtract it, it becomes plus 8. So we're going to have 16 minus 1/3 of 16. So we can use a common denominator of thirds. Whoops. And so we'll end up with 32 thirds. Okay. So really, there's no surprise there. Um, I guess they just wanted to illustrate theoretically what's happening here. But yeah, I mean, so it also illustrates, like I was saying before, because we don't need to subtract a second function because the second function is just y equals 0 anyway. So it amounts to the same thing. So implicitly, that is what we're doing, but it doesn't need to be shown when we have the horizontal axis as one of the two functions. All right. Um, so they want us to try one of these and see how far we get. So let's try this example just to get some practice. Y equals x squared and y equals 72 minus x. Now, of course, one is a parabola, one is a straight line. So there'll be 2 points where they cross. Let's now in the book, what they've been doing is they make sure that the one on top is designated f of x. It's not absolutely necessary, but I think it's a good practice. So of course we have to figure out where they cross. X squared equals 72 minus x. Let's gather them all onto the left-hand side of this equation. And you can either use the quadratic formula or you can try to factor it. If you do try to factor it, remember what you're trying to accomplish is we need two integers whose product is negative 72, which could be, for example, 2 and negative 36, negative 2 and positive 36. We could also have 3 and 24. 4 and 18. 6 and 12. Um, what else? 8. 8 and 9. Now, of course, they also have to add up to 1. So, in other words, the product is negative 72. The sum is 1. So that means we're going to pick these two. And you can multiply these out with FOIL and confirm that they are in fact the same. And now we set these equal to 0. And so what this is telling me is that the 2 points of intersection are -9, whoops, and +8. Yeah, this mouse is a lot faster than any mouse I've ever owned. So occasionally it gets a little away from me. So anyway, -9, +8. Let's look at that in the graph. So now I probably didn't, maybe this isn't so bad. Let's see. Yeah, that'll do the job. All right. So now what are we going to do? Well, we're going to integrate. And of course, I made sure that the f of x is the one on top. And also, we know that they're continuous. We can see that. Any polynomial, there's a theorem in calculus that says that all polynomials are continuous everywhere. But, we can go find that if you want, but we don't have to bother checking because we know that these are both polynomials. But anyway, so the top curve is the straight line, 72 minus x. And the bottom curve, the parabola, is just x squared. Okay. And the range of values is from -9 to 8. So we can simplify this. So what do we have again? 72 minus x. Hold on. Actually, let me drop that parenthesis. 72 minus x squared. That's better. And that is going to be integrated over the interval from -9 to 8. Let's rearrange it slightly. All right. And then, like before, we'll just break it up into individual integrals. Apply the power rule. And then even then we can simplify it just a little bit more. All right. Then we have, we start to evaluate these. Here we have 8 cubed minus, minus 9 cubed minus 1/2, 8 squared minus 9 squared. Yeah, that's right. Let me just make it a little neater. And then finally we have 8 minus 9. All right. So here we have -1/3. So a cubed is 512. Now here I'm subtracting out -9 cubed is negative and I'm subtracting. So whatever this number is, it's positive. 9 to the third, which is 729. Now, of course, negative 9 squared is 81, so I'm subtracting 81. And then we have 8 plus 9. And let's see, what is this? So 512 plus 729 is 1241. So we have negative 1241 thirds. Then here we have negative a half times negative 17. And then here we have positive 72 times 17. Let's clean this up a little. And 17 times 70, 72 times 17 is 1224. All right, so we will need a common denominator, which we'll choose to be 6. Okay, so this one becomes negative 2482 thirds plus 51 thirds. And this one, 1224 times 6 is 7344. Oh, sorry, this one is 6. I just realized I didn't write the sixth in here. All right, so let's see what we end up with. 7344 plus 51 minus 2482, 4913 over 6. I don't think that we can reduce that any further. Let me just confirm that. No. Okay, so that's it. So that's the area between here. Okay, very good. All right, now I think they have one more for us, one where we go from left to right. I'm sure we could use the practice. It's just a little bit 4913 over 6. Yeah, that's right. Um, the only thing is when you look at something like this, it's going to be tricky to determine, oh, no, one of them is 0. Now that's interesting. Huh. I was going to say it might be difficult to visualize which one is in the right and the left, but that's when we can lean on Symbol Lab. But let's do that anyway. I want to see what they're doing here. Um, so this one is because it's all in terms of y. That's how you know to go from right to left. Um, although later on we'll see that we can always go either way. But here they specifically are asking us to do it from right to left. And so the endpoints are negative 12 and positive 13. All right, so I'm going to go to Symbol Lab and just make sure that we're doing this correctly. F of y equals y squared plus 12. Now, I don't know if I know theoretically the Symbol Lab could show two different functions at once, but I've always had trouble doing that. Let me just do this. See what this one by itself looks like. Oh, okay. See, it's not expecting that. I'm going to do. Let me see if this is going to help. Um, Let me change this to X and see if that helps. It wasn't, it was very confused. You could tell it didn't know what to do. There we go. So, wow, it's way over here on the right, isn't it? All right. So now you notice how the other function is g of y equals 0. Okay. So, you know what we're going to do? I'm going to go to Desmos. I find that for the really messy ones, Desmos works a lot better. I don't know what the problem is with Symbol Lab. I just find it to be very awkward sometimes. Um, so we're going to do this one more time. F of y equals y squared plus 12. And then we have g of y equals 0. Okay. Okay. So that's what it looks like. And they want us to cover the area. So I have to assume what they mean here is they're asking us to cover the area between negative 12 and positive 13. So it looks like what they're after is this. And then let's say 12, 13 is here. And y and negative 12 is down here. And so it would be this area. Okay, so the important thing is that the f of y is the one on the right. Okay, that's really what we need to establish. So this area will be everything from negative 12 to positive 13, f of y minus g of y dy. And now we just plug in what we have. And so once again, that's y squared plus 12 minus 0. All right, so this is will be the easy part, integrating it. The setup was the awkward part. And so we'll use the usual techniques. All right, let's see what we get. Actually, so that will become y cubed over 3, evaluated between negative 12 and positive 13, plus 12 times y. Okay, let's try that. And yes, one more time. I'm just going to get rid of that 1/3 there. All right, now we substitute. Okay, great. All right. Now, 13 cubed is 2197. Now here, when I cube -12, it'll become negative, and when I subtract that, it'll become positive. So I'm adding whatever 12 to the third power is, 1728. Now, of course, here, when I subtract -12, I'm adding, so I'll end up with 13 plus 12. All right, so we got 39 25 thirds plus 600, 300 rather. I'll convert these all to thirds. Let's see, can we reduce this? No, it doesn't look like it. Okay, 48 1/4 thirds. And that would be B. Okay, great. Okay, so that's the end of that section, 7.1. Now 7.2, which we're not going to do just yet, we'll do it in the next session, is all about, yeah, this one's a little bit messier, because what's going to happen here is that we're going to not work with areas any longer, but volumes. Okay, so that does make things a little bit more challenging. Volumes. Okay, but so that's what's coming next. So we'll do that in our next session. All right, and I'll see you then.